I am Shyam Kumar from Government College of Engineering, Bargur, Department of Electronics and Communication Engineering. This is my first project at EMERTXE, the project Realtime EV and ADAS dashboard. Today we are going to see an STM32 Blue Pill and low-cost ARM Cortex-M and a Python dashboard, and see an introduction. What is EV? Electrically powered vehicle with battery, motor and power electronics. What is ADAS? Advanced Driver Assistance System. Safety, driver aids and automated alerts. Why real time? Immediate detection, response, reduce risk, improves performance and safety. Role of embedded system, sensor acquisition, low latency processing, and reliable communication to dashboard. Problem statement. No single low-cost certified dashboard for EV ADAS telemetry. Drivers lack time visibility into battery, motor and safety states. Motor overheating and battery faults can go undetected until failure. Collision and blind spot risk require fast, reliable detection. Design objectives: real-time monitoring, battery SOC. SOC means state of charge, motor temperature, ADAS detection, system architecture, sensors, UART, STM32 Blueprint, low latency ADAS logic, real-time visualization, Python dashboard, raw ADC and GPIO data. Now we are going to see the hardware components: ultrasonic sensors, potentiometers, indicators, UART and PC. Software stack: STM32 Cube IDE, embedded C for firmware, PixSim Lab for hardware in the loop simulation, Python for dashboard and data processing, virtual COM tools for serial bridging. Dashboard monitoring, monitored parameters, vehicle speed, battery SOC voltage, motor temperature, torque, estimated driving range, brake acceleration, position, fault, alarm status. UI goal, design goals, low latency updates, clear alarm hierarchy, compact dashboard cards for rapid scanning. And ADAS features: forward collision warning, blind spot detection, motor overheat protection, fault and obstacle detection, and communication and results. Key results: real-time Python dashboard, reliable UART comms, function collision, blind spot detection, unaudible visual alerts. Future scope: CAN bus and camera vision integration, GPS and IoT cloud sync, predictive maintenance, mobile app and real vehicle deployment. Advantages and applications: low cost, modular, fleet monitoring, ADAS research, suitable for internship, Viva and prototype demos. Okay, let's now we can start the project with the Blink starting open project, and we can see the binaries, includes and core and drivers debug. Let's open the core and see the inc file. Let's main.h. We can see the main.h file, and the src file. We can see the main.c file to see the main code, and the header main and the code main. Okay, let's debug using blink.ioc. We can see the blinking file. It was loading. Now after loading, we can see it in a PixSim lab. Okay, yeah, we can see the pin configuration like this. Yes, pins GPIO output pin 13. We are connecting to this, and now we are adding a PixSim lab to generate this output. Okay, let's see the output in the PixSim lab. Yeah, in the PixSim lab, IO we can put it in 8 and CPS EMS 31.25. Then we go to file and load pin. The project we can do is blink, open the blink folder, and then debug blink.binary file. We can open the binary file, then it loads and the LED is blinking. This is our first project. In the same way, in the same way, second ADC, same like debug, like adc.io, the load files loading. Yes, we can see the connections here. And now you can go to that old button preference. Yes, you can see the preference, and now appearance, show you others. It's like that. Okay, let's do the Pixim lab. Load bin. We can second project ADC, same like ADC debug, ADC pin, and we can start. You can see the output here. Now we can connect the spare parts here to see the output. Yes, this is our final EV dash output before we are doing the simulation. Let's we check the output. Double click. This is the potentiometer. Going to input and select the potentiometer round or rotatory, and this is the virtual IO term, and this is the ultrasonic sensor front sensor, and this is a left and right sensor. We can change the values. This is an LED. We can like, and doing this we can going to others, sorry, virtual and text box. We can add this as, and we can see the final output. We can zoom and zoom out. Now we are going to see the final result of the project. Yeah, now in the same way we can do timer program, and we can open a AV dash core src, and we can see the adas.c, adas.h, and main dot open main.c, adas.c, adas.h, all files. We can paste the code, and we can see the ultrasonic sensor.c and ultrasonic sensor.h. Everything we can check and check the code until it's any error, and we can see the adas.c, adas.h, and ultrasonic UART shell.c, ultrasonic sensor.c, can see etc. Every files, and we can see the Pixim lab simulation. Yeah, we can changes, see the changes in the, we can make a change in a front sensor, and we can see the temperature increase, and we can click, and we can the yellow LED will blink. We can reduce the yellow LED blink will off, and we can reduce the and increase PA1, PA0 acceleration and brake and state of charge. See the yellow LED will on, and we can see the output as like speed, and we can continuously see the output. We are moving around, and we can reduce it again temperature and increase in left and right ultrasonic sensor, and we can reduce the front. Yeah, we can see the red LED and yellow LED will on. You can see the output in the virtual terminal. Yeah, the output will flow, and we can reduce again left. Yeah, now let's see the EV ADAS dashboard. See the speed 71 kilometer per hour and speed history 75, and we can see the mode is normal, and we acceleration. Let's see the brake acceleration 92 and alarm none. ADAS bird eye view 233 centimeter between the your car and another car. Let's see the front distance, left distance, right distance, and the dashboard shows torque equal to 0 Nm and acceleration equal to 92 percentage. Brake not applied yet. One now change torque is 138, and let's see signal is on, and the speed is 68 kilometer per hour. And the speed history little bit variation in it. and we can see the battery 93.6 percentage. Now let's see the Pixim lab with the potentiometer change in the temperature. We can raise it into 2.11 and 2 point something. We can see the yellow LED fault. And now see